Hello, welcome to another edition of TutorTube, where the Learning Center's lead tutors help you understand challenging course concepts with easy-to-understand videos. My name is Kelly Schmidt, lead tutor for statistics at the Learning Center. In today's video, we will explore a few of the fundamental topics and skills related to the normal distribution that will help you to be successful in your course. Let's get started. When we're working with data that follows a normal distribution, one of the most important concepts to understand is the z-score. The formula for z-scores for samples is z equals x minus x bar over s. And why do we need z-scores? Here's an example. Let's say we have classes of students taking the same class with two different professors, Professor A and Professor B. Professor A gives his class a test, and overall the class does pretty well. The average is a 75%. However, Professor B also gives a test, but this test is much harder. The class average is only a 40%. Let's say I'm a student in Professor B's class, and I know that I got the highest score on the test at a 65. How do we compare my performance to the performance of students on Professor A's test? My score of 65 was less than the class average for Professor A, but it was still the best in my class. You can't judge my performance on the same scale as the students in Professor A's class. We need some way to represent the situation, and that's where z-scores come into play. Using z-scores allows us to standardize scores so that we can compare them across populations that have different means and standard deviations, as long as they follow the normal bell-shaped distribution. Let's do a practice problem to see how this works. Here's a common question that you'll see in this section. Mark finished first in last year's annual race in 16.2 minutes. The average time for last year's race was 18.2, with a standard deviation of 2 minutes. Sally finished first in this year's race in 16.7 minutes. The average for this year's race was 20.3 with a standard deviation of 3. Who did relatively better? Okay, first off, notice the phrase relatively in this question. They aren't asking who had the fastest time, they are asking who had the fastest time relative to other runners in their race. Because of this, in order to answer this question, we need to find the z-scores for Mark and Sally. Recall that the z-score formula is observation minus mean divided by standard deviation. First, let's find each of these values for each runner. For Mark's race, the mean was 18.2 and the standard deviation was 2, and his score was 16.2. For Sally's race, the mean was 20.3, the standard deviation was 3, and her score was 16.7. Now let's calculate Mark's z-score, which we'll label z sub m. Z sub m is equal to 16.2 minus 18.2 divided by 2 equals negative 1. So we can say that Mark had a standardized score, a z-score of negative 1. What does this tell us? Well, we know now that Mark's time was 1 standard deviation faster than the average score in his race. Not bad. Next, for Sally's score, which we'll label z sub s. Z sub s is equal to 16.7 minus 20.3 divided by 3, which equals negative 1, or negative 1.2. So we can say that Sally had a standardized score of negative 1.2. What do these scores mean? This tells us that Sally's score was 1.2 standard deviations faster than the average time for her race, which is even better than Mark. So we can answer the question by saying that even though Sally had a slower time, she actually did relatively better than Mark during her race. Next, let's look at the empirical rule. This is a concept that will come up a lot when you are working with a normal distribution. The formal definition of the empirical rule is this. If the shape of the distribution is bell-shaped, aka normal, then approximately 68% of the data will lie within 1 standard deviation of the mean, approximately 95% of the data will lie within 2 standard deviations of the mean, and approximately 99.7% of the data lie within 3 standard deviations of the mean. What does this mean? Well, the simplest way to think about it is as we move farther and farther away from the mean of our distribution, the less likely we are to see an observation that extreme. For example, since we know that 99.7% of all of our data typically lie within 3 standard deviations of our mean, the odds of seeing an observation more extreme than 3 standard deviations above or below would only be 0.03%, which comes from subtracting 99.7% from our total 100. Let's do some practice problems to see how this rule helps us out when we're working with data. Scores on an IQ test have a bell-shaped distribution with a mean of 100 and a standard deviation of 14. What percentage of people have an IQ score between 86 and 114? The first step is to build our distribution using the values that they give us. The mean is 100, so we place this value in the center. Next, since the standard deviation is 14, we find the values of the tick marks on either side of the mean by adding and subtracting 14 from 100. 100 minus 14 equals 86. 100 plus 14 is 114. So we know a score of 86 is 1 standard deviation below the mean, and a score of 114 is 1 standard deviation above the mean. Now back to our question. We want to know the percentage of people between 86 and 114. Using the chart here, which is a simplified version of the empirical rule that I prefer to use, all we need to do is add the percentage values between our two values. 34 plus 34 equals a total of 68%. Now for part B. What percentage of people have an IQ score less than 86 or greater than 114? This question is actually asking us to find two different areas. The first is the percentage of scores less than 86. We can do this by using the same chart we just made. Adding all of the percentages to the left of 86, we get 13.5% plus 2.35% plus 0.15% equals 16%. Similarly, if we want to find the percentage of scores greater than 114, we simply add all of the percentage values to the right of 114. 13.5% plus 2.35% plus 0.15% equals 16%. Combining these two values together, 16 plus 16 gives us a total answer of 32%. Next, part C. What percentage of people have an IQ score greater than 142? For this question, we need to find the location of a score of 142. We know it's larger than the mean, but we don't know if it's 1, 2, 3, or more standard deviations above. Let's start by finding the values on the next two tick marks on our distribution. 114 plus another 14 equals 128. So we know that 128 is 2 standard deviations above the mean. Now we repeat again. 128 plus 14 equals 142. So we've found the value that we're looking for. 142 is 3 standard deviations above the mean. Now we can simply add the percentage values greater than 142 to find our answer. This is only one value in this case, 0.15%. We can also use the normal calculator in StatCrunch to find the answers to the problems we just completed. In StatCrunch, we go to Stat, Calculators, then Normal. This will open up the normal calculator. Let's say we wanted to find the answer to part C. What percentage of people have an IQ score greater than 142? First, we enter the values for the mean and the standard deviation we were given. Here, that was 100 for the mean and 14 for the standard deviation. Next, since the problem wants the proportion greater than 142, we change the sign to a greater than or equal to, and then enter our value of 142 into the box. Now we just hit compute. We can see that the answer given is 0.0013499, or about 0.135%. Notice that this is not the same answer that we got when we used the empirical rule, which was 0.15%. This is because StatCrunch gives us an exact answer, while the empirical rule only provides us with estimations. Now let's say that we wanted to find the answer to part A. What percentage of people have an IQ score between 86 and 114? The key word in this question here is between. Since we want the area under the curve between two values, we need to select between option at the top of the normal calculator. From there, we simply enter the two values at the lower and upper end points of our interval, 86 and 114. Then click Compute. Again, notice that the answer we come up with here, 0.6826, is not exactly 68%. However, it's pretty close, which means that the empirical rule is able to give us a pretty good approximation of the exact values without the use of technology. Alright, so with that we've finished all parts of our problem. I hope you found this to be a good introduction to Z-scores and the empirical rule. Thank you for watching this TutorTube presentation. Please subscribe to our channel for more exciting videos, check out the links in the description below for more information about the Learning Center, and follow us on social media. See you next time.